We've just talked about what an acid is and what a base is. So what if something is both? Then we call it an amphoteric substance. Amphoteric. Kind of a fun word. So what an amphoteric substance is anything that'll be able to act as either an acid or a base because it both has a acidic hydrogen that's transferable or donatable and an atom that has a lone pair of electrons that can accept a hydrogen proton and form a bond to it. And so there's actually lots of things that have this ability, but one of them is the most important of them all, and that's water. Water has two lone pairs and it has two hydrogens. Both of those hydrogens are bonded to something that's more electronegative, an oxygen. And so these are pretty partially positive hydrogen atoms, and these lone pairs are on an oxygen that's very electronegative. And so it has a partial negative charge that'll be able to easily attract hydrogen ions to it, right? So we see water act as an acid when it loses a hydrogen. And so here we go. We have our hydrogen acting as an acid. It donates a hydrogen and it forms hydroxide ions. And then at the same time, our water molecule can accept a hydrogen, and this is when it's acting as a base. And then it forms a hydronium ion. And so when it can do both, which one does it do? Well, it's going to do whatever it's paired with. So if you add an acid to water, it will act as a base. And if you add a base to water, it will act as an acid. And so water is able to kind of switch its role based on the context it's within, which is its superpower. Um, and so we oftentimes evaluate and talk about different acids and different bases based on how they behave in water, since it can be either an acid or a base, and it's also a great solvent, right? And so this will allow us to track general acid strength, and we'll talk about that in terms of equilibrium here in a bit. But we're going to start by just predicting what happens when you add an acid or a base to water. And it's similar to our neutralization reaction, so that we're just going to shift a hydrogen from the acid to the base. But we're not going to call it a neutralization reaction because our pH is not going to become neutral. In fact, if we add an acid to a water, it'll stay, the whole solution will become acidic. If we add a base to water, the whole solution will become basic. And so we're going to call these acid and base dissociation reactions. And so here's an example. So looking at our acid dissociation reaction, we'll see that when we add an acid like hydrochloric acid, our water will act as a base. It'll then accept that hydrogen atom from the hydrochloric acid and form the conjugate acid, hydronium. Now, in a base dissociation reaction, we add a base to water. And in this case, we're going to look at ammonia again. And so here we're adding a base to water. And our water then is going to act as an acid. And it's going to donate a hydrogen to the ammonia and form a conjugate base product. And so when an acid or a base is added to water, we form a solution, acidic or basic solution. Typically, it's the H3O plus or the hydroxide ion that really drives the overall acidity or basicity of that solution because the acid or base itself is reacting with the water. And when we actually go to characterize like how acidic or how basic something is, we're in fact going to use this hydronium ion concentration and hydroxide ion concentration to characterize it. And so that's going to be the foundation of how we assess if something's an acidic solution or a basic solution. Here's an example. You can try it on your own first if you want to pause this, but we're going to try to predict the products of the acid dissociation below. It looks like, sorry, the base one didn't print. I'll write it out. So here we have nitric acid and water. So when I look at this, I see H, N, and O, and I'm like, oh my gosh, like, is this an acid or is this a base? Well, that hydrogen is going to, this kind of helps to know the structure sometimes. That hydrogen is actually going to be bonded to an oxygen, to the nitrogen, and we're going to have an oxy acid like this. So when this forms, what we're going to do is we have this acidic hydrogen right here, and it's going to transfer to our water. So our nitric acid right here, and our water is going to be then acting as a base. So when I write out my products, I'm going to make sure that I'm writing out my acid minus a hydrogen. So I'll have NO3 minus because I lost that proton and left its electrons behind, giving it an overall negative charge. And this is now my conjugate base. And then I'm going to add a hydrogen to my water to form my products. And so that's going to be H instead of 2O, it'll be H3O. And it just gained a proton, so it's going to have an overall positive charge. And this is my conjugate acid. Let's look at an example of a base dissociation. These ones are a little bit simpler, or they're kind of funny because they feel repetitive. So, or at least ones with hydroxide ions. So here I have potassium hydroxide, and this is my base. So since I've added a base to water, that means my water will act as an acid. So one of these hydrogens from the water is going to transfer to the lone pair on one of my oxygens that has that overall negative charge, since this is an ionic compound. Remember, when we're looking at ionic compounds, we can really think of this in water as a potassium ion plus a hydroxide ion if it's soluble in water. So when this happens, I'm going to write my base now with an extra hydrogen. And so this would look like, and I'm going to go through a couple steps here, right? This would, if I was just adding the hydrogen, it would look like KOH2. So I'm going to stop here. So when we had our potassium and our hydroxide in water, they separated, right? And so what's really our base here is the hydroxide ion and not the potassium. It's just hanging out. It's a spectator ion. It's not really participating in this reaction. And so it won't make sense to write this because my OH2 is neutral and my potassium has a positive charge. So overall, this would have a positive charge, and my cation is not going to form an ionic bond to something with no charge. It can only be attracted electrostatically to something with a negative charge. And so this doesn't work. And it's a common mistake when you're learning this because we get used to just shifting that hydrogen over. But when we're looking at these as chemical formulas, it's sometimes easy to forget that, oh, actually, this is in water. So this potassium hydroxide is not really a potassium and an oxygen and a hydrogen all bonded together. They're separated out. Got a Van Hoff factor of 2. So what this is really going to look like is the OH2 part. And you can write OH2 if you want. But typically what we do when we write this is we write H2O. That's how we write for water. And it's going to be far more recognizable to you as water, which I know is a rearrangement of how we're writing it when we do hydroxide. So I like using OH2 or H2O. And then after that, we'll be left over with our water minus a hydrogen, which will be OH minus, right? So our hydroxide had a negative charge and it formed a bond to a hydrogen, so it became neutral. Our neutral water lost a proton, and so it became negative. And so we'll have this OH, and then we have our potassium still hanging out, right? And if you want, you can combine these and write KOH again, which is why I said this sometimes feels a little repetitive. Like you can write this as KOH plus H2O forms H2O plus KOH. And really what's happening here is that our hydroxide ions are just soluble in water, and our ionic compound breaks apart and we have hydroxide ions floating around. And what is constantly happening, even though it just looks like the same amount of hydroxide ions from that macroscopic big picture, is our hydroxide ions are constantly pulling a hydrogen off of a water and forming water and creating a hydroxide that then pulls a hydrogen off of another water. And this is just happening constantly within the solution. I almost think of it as like waters and hydroxide ions and these little protons just kind of like pinging around amongst these molecules, just kind of changing where they're bonding. And especially when you think about all these things as vibrating, right? Like those bonds are constantly stretching and vibrating. And if they just stretch longer, suddenly it's stretching closer to another molecule and it's formed a bond to that.